Dr. Giovanna Ferraioli first will give us her presentation on the physical background of shear wave elastography. And Giovanna did a great effort and activity for our EFSUM guidelines. And warm welcome, Giovanna. We very much looking forward to hear your presentation.
Thank you so much, Christoph. These are my disclosure, and elastography technique shows the biochemical properties of tissue, whereas the B-mode ultrasound shows the acoustic properties of the tissue. And these properties are not related to each other. Elastography can be seen as a virtual palpation. Under stress, the stiffer tissue shows a less longitudinal displacement, and there is a higher speed of a transverse displacement. So to perform elastography, there is first of all a stress, and this stress causes a change in the shape, and then the software of the system measures the tissue displacement over time. There are two techniques. One is based on the longitudinal displacement of the tissue, and the other one on the speed of the transverse displacement. As for the longitudinal displacement, we have strain elastography and acoustic radiation force impulse imaging. Strain elastography is a quasi-static method. Force is applied by pressing the body with the probe axially, or using the motion of a structure that naturally moves inside the body. In strain elastography, the internal tissue displacement is converted to a strain image, that is the percentage of deformation. Because the percentage of deformation is constant, instead the displacement decays with depth. And using strain elastography, the image, of course, with depth is more clear. It is possible also to use the force of the ultrasound beam, as it is in the acoustic radiation force impulse imaging. In this case, a focused ultrasound beam and the force of this ultrasound beam is used to generate a localized displacement in the ultrasound axial direction. So to summarize, the techniques based on the longitudinal displacement are strain elastography, and in this case the longitudinal displacement is measured as strain, or the acoustic radiation force impulse imaging, and in this case the longitudinal displacement is measured without any further processing. These are the images that obtained with strain elastography and acoustic radiation force impulse imaging. These are qualitative images, and indices can also be obtained. However, in strain elastography and ARFI imaging, the quantity of the stress is unknown. Thus, it is not possible to obtain a quantitative measure of the stiffness. As for the shear wave elastography, the methods for generating the shear wave displacement are the force of the ultrasound beam, so the ARFI, as in point shear wave elastography, two-dimensional shear wave elastography, or an external mechanical stress, as it is used for transient elastography, but also for magnetic resonance elastography or vibroelastography. The US shear wave elastography techniques are or ARFI-based, or we have the FibroScan, the transient elastography. When we use the force of the ultrasound beam, this is the stress that is used to create a displacement with the ultrasound, and these beams have a pulse that is longer than the pulses used for the beam of the image. And the purpose is to generate a local micro-level tissue displacement. And shear wave formation caused by the force of the ultrasound beam propagates as shear waves. And the software of the equipment measures the velocity of the shear waves propagation. The shear waves in soft tissue, they have a speed that is much lower respect to the speed of the ultrasound beam, and they attenuate very fast. And using a point shear wave elastography, the assessment is of the stiffness or the velocity of the shear wave is made in 1 point. There's a regional value of shear wave stiffness or the speed. Instead, using the two-dimensional shear wave elastography, also images of the elasticity are obtained. There are several manufacturers that have developed the point shear wave elastography and two-dimensional shear wave elastography technology on their equipment, and the registered name is different depending on the manufacturer, but the technique is always the same. The force of the ultrasound beam, that is the ARFI pulse. In a point shear wave elastography, the strongest part of the ultrasound beam is at the focal point. This is where the pushing is made, and shear waves are generated, and they propagate in a cylindrical symmetry away from the pushing. The ultrasound imaging is used, so the beam mode is used only to guide the placement of the sample box, but no elasticity images are obtained. And these are the technology that are available so far. As for two-dimensional shear wave elastography, we should think that is obtained using several ARFI lines, and shear wave arrival time is detected at multiple lateral locations. These are the two-dimensional shear wave elastography technique. The sample box is adjustable by the operator, and measurements are performed using an ROI that is put inside the sample box. Every manufacturer has its own quality factor that should be followed by the operator. SSI is different from the other methods because it's a true real-time shear wave elastography, and it uses a proprietary radiation force technique that is termed supersonic shear imaging. And in the supersonic shear imaging, it is possible to reach a frame rate that is very high, very fast, is more than 1,000 frames per second. So the focus is simultaneously obtained in several points, and shear waves also, they propagate together, and this is possible in this way to obtain a cone that decays less rapidly with the distance respect to a single pushing focus. In transient elastography, the stress is external and is controlled. The pushing is at 50 Hertz, is a vibration at 50 Hertz. There's no images of the lever, and there's a line, a diagram, and in this case the white dotted line represents the propagation velocity of the shear waves, and the slope of the white line increases in function of the fibrosis stage. In shear wave elastography performed with the FibroScan device, the shear waves are traveling along the longitudinal axis to the lever. The measurement is performed in a fixed position of the lever, and with the M probe, it is at 2.5 centimeters from the skin, and at 3.5 centimeters from the skin with the XL probe. The unit of measure that we use, we are elastography in the ARFI method. The shear waves are generated, so there's a velocity of the shear waves in meter per second. This velocity can be converted into stiffness using the Young modulus or the shear modulus G. But to perform this conversion, we assume that there's no variation of the frequency of the applied force, no variation of the velocity on the position or direction of the tissue, and so we convert. However, these assumptions are not always true. The modules are measure of the stiffness, and Young modulus indicates how difficult it is to deform a material by stretching or compressing it, and the unit of pressure is kilopascal. The shear modulus has the same unit of pressure in kilopascal, but it measures the ability of a material resist a transverse deformation. The two modules, the shear modulus G and the Young modulus E, are related to each other. However, we should keep in mind that the Young modulus is 3 times the shear modulus. So even though the unit is the same, the value that we obtain at the same stiffness are not the same. Usually with the ultrasound equipment, the Young modulus is used, and instead with magnetic resonance, the shear modulus is used instead. The choice of whether to display the speed or modules is under user control in the majority of the equipment. In some cases, this choice may be unavailable. It may also depend on the regulatory authorities for the region of the world in which the system is sold. From a technical point of view, it is preferable to report the results in meter per second rather than in kilopascal. In fact, this is the unit that the system quantifies, the velocity of the shear waves. The conversion in kilopascal using a simple equation is based in many assumptions that may not all be correct. However, the measure of stiffness using the Young modulus in kilopascal has become quite popular in the clinical practice since the availability of the FibroScan, and it is used in most parts in the world. There are factors affecting the quality of the shear wave, the quality of the measurements, and that can produce errors or loss of signals. And it's the strength of the push of the ultrasound beam, the variations in attenuation, and the absorption and reflection of the pushing beam, as it could happen in liver steatosis, the density of the scatterer, a very high or very low shear wave speed, the scattering of the shear wave itself, and the reflection or the refraction of the shear waves. We have to keep in mind that we assume that the tissue are elastic, linearly elastic, homogeneous, isotropic, infinite, and continuous. But the biological tissue are much more complicated. We have viscoelastic material, not elastic material, and using elastography, we are assessing only the elasticity. The viscosity as of today is not taken into account. So in conclusion, we have three options for displaying the mechanical properties of tissue. Display the axial displacement without any further processing, and this is the ARFI imaging. Display the tissue strain calculated from the percentage of displacement, as in strain elastography, or display the shear wave speed, measuring the time of arrival of the shear wave at various locations, as it is done in point shear wave elastography, two-dimensional shear wave elastography, real-time two-dimensional shear wave elastography, and three-dimensional shear wave elastography, and also in transient elastography. Using the Young modules, the measure of stiffness could also be displayed. Thank you very much. And
oh, Giovanna, that was great to make physical principles so easy to understand. I very much enjoyed your lecture. That was great. And so there are, the audience is very much interested in all that talks and presentations, and I would love also to raise a few questions from the audience all over the world. So the first question, I'm not quite sure if we can easily answer this, is what differences area are there in liver metastasis after radiofrequent ablation in 1, 3, and 6 months? So this might be a question we all cannot answer. So after radiofrequency thermoablation, what do we expect in liver stiffness of such lesions over time, if I understood that question right?
May I answer the question from my point of view, and also looking at the literature, the assessment of focal liver lesions using elastography has given conflicting results. So sometimes there's an increase of stiffness of the lesion, sometimes a decrease of the stiffness. This is a field still open to research, and we are looking forward for the literature.
What is the accuracy of splenic elastography? Do we have splenic elastography in daily routine? What is the accuracy of this method?
May I answer the question?
You have the first three, and then we will we'll go through the others as well. So for the moment, you have two more questions to get answered.
Okay, so these are all questions for me. I was,
yes, only for you.
Okay, I was waiting for the technical questions, and for that reason I was a little bit bewildered. But it's okay, it's okay. As for the spleen, our group performed a study assessing the repeatability of measurements of the spleen in normal spleen, and agreement between different operators is lower respect to the agreement that is obtained for the liver. There are several studies published, however, the percentage of failure in all the studies is higher respect to the measurements performed in the liver. The accuracy in assessing portal hypertension has been assessed comparing the results to a gold standard, that is the measurements of the pressure in the portal system. So the method is from the literature, an accurate method. It's more difficult than liver elastography to perform. It's less reproducible, but it's an accurate method.
And the next question would take to answer about half an hour, but you have only 60 seconds to do so.
I'll try.
How can you evaluate different indicators of elastography in different equipments? So not only from one company.
Usually in the clinical practice, generally the operator uses only one, and each company has its own reliability factor, quality factor that should be used. From my point of view, all the companies have developed a good quality factor that should be followed before taking into account also the recommendation of the guidelines. I hope I answered the question.
Thank you so much.